Hello everyone, welcome to our discussion of section 7.5 where we will be discussing how to use integrals to calculate the area of a surface of revolution. Now as you can see on the screen, we've already talked about how to use integrals to calculate the volume, the length of a curve, and now we'll apply some very similar method here to calculate the surface area of a solid of revolution. Now there are two cases that we may consider. One is on the left here on the screen is if you have a surface area that you are calculating when rotating a region about the x-axis. So if that's the case, then the generalized integral would be the surface area, and of course this would be definite integral. So let me just say a to b. I guess I try to match my notation to what your books has, but these are both definite integrals, so we will have limits here. 2 pi y ds, and that's if the rotation is happening about the x-axis. If the rotation is happening about the y-axis, we will have integral of 2 pi x ds. Now ds itself has this form, either this formula or that formula, depending on which variable we're using in our integral. If we're taking the integral with respect to the x variable, this is what we will use. If we're taking the integral with respect to the y variable, this is the ds formula we will use. Which variable we're integrating depends, it makes no difference, it's just whichever one is easier to integrate is what will determine whether we'll use this one or that one. But either one can be used in these formulas. However, if we have a rotation about the x-axis, this is the one we'll use. If rotation is happening about the y-axis, this is the one we will use. You've already seen these, right? This is when we talked in the previous section, 7.4, when we talked about how to use integrals to calculate the length of an arc. This is what we used, right? So we're using them here in the context of this new integration formula. Okay, so let's go over some examples here. So we want to find the exact area of the surface obtained by rotating the curve, this curve in this case, about the given axis. So about the x-axis, and I've already written down here, since the rotation is happening about the x-axis, this is our formula. And so looking at what we've been given, it's better to, if we're integrating about with respect to the x variable, let's solve this equation for the y variable. So let's do that as our first step. So we have, if we have from that, we have y squared equals 9x minus 18. And then of course we have y equals plus or minus square root of 9x minus 18. So here, note that we have plus or minus, but our decision to whether to use the plus one or the minus one or both is simplified, because if you graph this, so and I hope you do this as you watch this video, graph this expression on desmos.com, the website, and see what kind of graph you'll get. You'll see that the graph of this is symmetric about the x-axis. So let me make a note of that the graph of the original expression, 9x equals y squared plus 18, is symmetric about the x-axis, which, by the way, is our axis of rotation, i.e. the axis of. So this simplifies things, because if you take the positive or the negative part of this and you rotate it about the x-axis, since the whole thing is symmetric about the x-axis, then you're rotating one half over the other half. So in the end, it makes no difference. So we'll just use the positive portion of this. Okay? And so because of this, we will use the positive value, and this would be the top half of that graph. When you do that, when you graph this on the computer, the top half for the rotation. Okay, so let's do that. And so the first thing we want to do is find, if we look back at this formula for ds, we're going to have to find the derivative of y with respect to x to use in this formula. So let's do that first. And I'm going to start with the positives. So let me move this up. So given this, so this is now becomes 9x minus 18 to 1/2 power. Therefore, dy dx will be 1/2. So let me do it step by step. So 1/2 times 9x minus 18 to minus 1/2 power times, of course, by the chain rule, times 9. So let's simplify this a bit. What do we get? We get dy dx equals 9 over 2, and I will rewrite this back in radical form, square root of 9x minus 18. Okay, so we found this portion of the ds formula, dy dx. Now we're going to plug it in here. We're going to calculate 1 plus that squared, and then take the square root of it when we plug it back into the formula here. Okay, so let's do that. So now we have 1 plus dy dx squared would be equal to 1 plus all of that squared. Okay, so we'll get 1 plus 81, and this will be 4, and of course this power and this radical cancel, this square root cancel each other out, so we end up with 9x minus 18. Okay, when we take the common denominator, let me take this one step further. This is what we'll get. So 4 times 9x minus 18, and of course that would be the numerator is 36x plus 9. So 1 plus dy dx squared is that. Okay, now let's take this. Remember that we have to take the square root of this quantity, right? We did 1 plus dy dx squared. We have this inside quantity. Now we have to take the square root of it when we plug it in here for ds. Okay, so let's do that. We have s equals, of course, from 2 to 6, right, for the x variable. So we have integral from 2 to 6, 2 pi. Y is what we figured out in a few minutes. It's that one, right? Square root of 9x minus 18. that, times square root of all of this. Like that, and of course, let me not forget dx. Okay, so let's simplify things a bit. I'm going to put the 2 pi in front. Integral from 2 to 6. I'm going to keep this the same way. So square root of 9x minus 18. I'm going to distribute this radical over separately over the numerator and the denominator. So we have square root of 36x plus 9 over square root of 4 times, I should have done it right away, but it's okay. Like that. Okay, so now if we simplify this, we will get, notice that these two cancel out and we end up with just the 2. Well, the 2 also can, well, let me write it all the way. So we have 2 to 6. Times square root of 36x plus 9 divided by 2 times square root of 9x minus 18, right? So now it's easy to see that this 2 and this 2 cancel each other out. This whole term, this whole, and that cancel each other out. So we end up with just a small portion of that integral left for us to figure out, like that. So we're going to have pi left over, integral from 2 to 6 of square root of 36x plus 9 dx. Okay. Now that we can use, let u be 36x plus 9. So our du then would be 36 dx, which means dx is equal to 1 over 36 du. Okay. Since we're using this substitution, so we have to figure out the new limits of integration for the variable u. So if in this equation, right, in this equation, if x is equal to 2, we end up with 81, right? This is 72 plus 9. So u would be 81. If x equals 6, then 6 times 36, 216 plus 9, 225. So we have u equals 225. So let's set up our new integral given the variable u. So we have s equals pi from 81 to 225. And then, so instead of that, we have u to 1/2 power, or square root of u, right? And then instead of dx, what do we have? We have 1 over 36 du. Like that, right? Okay, so we're getting closer to the completing this. So we have pi over 36. And let's just integrate that. This is pretty easy to integrate. So 2/3 u to 3/2 power, 81 from 81 to 225. So then we have s, 2/3 times 225 3/2 power minus 2/3 81 half power. So, and what I ended up was pi over 36 times 1764, and that will lead to 49 pi. So pretty straightforward once we know how to use those formulas for ds and s. These calculations work out nicely. Okay, so let's do another example. I strongly recommend to please pause at this point and finish this all the way. Don't spend more than 15-20 minutes on this. And then, do your own work and then compare your solution with this, and hopefully our answers agree. And I count on you to let me know if you have any questions. I'm assuming you've done that, and now you're back, which is great, to compare your solution. So once again, we have the rotation about the x-axis, and for that, we will use this one, integral 2 pi y ds. So let's do that. So s ds. Okay, so we begin with this and calculate dy dx first. So we have y, and I'm just going to rewrite it in terms of a rational exponent. And then from that, we have dy dx would be equal to 1/2 1 plus e to the x minus 1/2 power times, of course, this e to the x. And then let's simplify this a bit. So we have dy dx equals e to the x divided by 2 times square root of that because of the negative exponent. So we'll find that in the denominator here, e to the x. Okay, so now let's calculate 1 plus dy dx squared. So that will be 1 plus all of that squared. And so we have 1 plus e to 2x power divided by 4. This power and this square root cancel each other out, so we have 1 plus e to the x. So we figured out all of this is the inside of this square root. So now we have to apply the square root to it as we plug it in for ds in our integral. Okay, so we shouldn't forget that. So let us do that. So we have s would be equal to 2 pi y ds. Of course, this is from 0 to 1, right, for the variable x. And I'll put here 0, and so this is our surface area. Okay, so then given that, we have s equals 2 pi. Y is simply that. We already have it here, or here actually, using the radical form. So let's plug that in. We have square root of 1 plus e to the x times the square root of all of this. Okay, so times square root of 1 plus e to 2x divided by 4 times 1 plus e to the x, and of course dx here. Okay, so now if we distribute, let's take the common denominator first. So I'm going to do that, common denominator underneath here. So we'll end up with s would be equal to 2 pi from 0 to 1 square root of 1 plus e to the x. And then if we take the common denominator here, we will end up with 4. So let me that here. 4 times 1 plus e to the x. So we'll end up with 4, right? 4 plus, and I'm distributing the 4 into this as I find the common denominator here, as I combine these two. So we end up with plus 4 e to the x, and then plus e to the 2x, okay, dx. Now, if we distribute this square root to the numerator and the denominator separately, we will get this. We will get square root of all of that divided by 2 times square root of 1 plus e to the x dx, right? So now this 2 once again cancels with this 2, and all of this cancels with this, so we'll end up with that. But this, okay, let's write it in simplified form. So we have s equals pi times integral from 0 to 1 of all of that, 4 plus 4 e to the x plus e to the 2x dx. Now this inside we can write in terms of a perfect square, fortunately. So pi from 0 to 1 square root of, and so we have 2 plus e to the x squared dx. Of course, this power and this square root cancel each other out, so we will end up with pi integral of 0 to 1 of 2 plus e to the x dx. Okay, and of course this is pretty straightforward to integrate. We have pi times 2x plus e to the x from 0 to 1. Okay, so let's evaluate this up here. We end up with pi and then 2 plus e, and then minus 0 plus, right, 0 plus 1. 0, e to 0 power is just 1, so we have that. So 2 minus 1 is just 1 plus e times pi. So we have pi times 1 plus e, or e plus 1. Okay. There we have it, like that. I hope this is starting to make sense, if it didn't already as you read the book. So, all right, so in this example, once again we have rotation about the y-axis. So immediately we know that we have to use this version of the integral, 2 pi y ds. And so let's start with that. So the first thing is just take the derivative of this. Again, I hope you're pausing before you're seeing my solution. So please take 15-20 minutes to solve this on your own. So I would rewrite this with the powers clearly shown. So I don't want to have x in the denominator in this form. It's easier to take the derivative of if we do that. So let me do that. Y equals 1 over 6 times x cubed plus 1 over 2 times x2 minus 1 power, right? Given that, we can then easily calculate take the derivative dy dx as, so 3 times 1 over 6, it's going to be 1/2 x squared, and then minus 1/2 times x2 minus 2 power. And then from that, we get dy dx equals 1/2 is common here. Let's factor it out. 1/2 times x squared minus x to minus 2 power. Okay, so this is our dy dx. Let's find out our 1 plus dy over dx squared. All right, so 1 plus all of that squared, 1/2 times x squared minus x to minus 2 power, and then squared. If we distribute the power here, we will get 1 plus 1 over 4 times x squared minus x2 minus 2 power squared. Okay, so we figured out 1 plus dy dx squared again. Let us use it in our integral for the surface area. So we have 2 pi y ds, right? So this will be, and of course this will be from 1/2 to 1, right? So 1/2 to 1. Okay, so we have s from, and I'll put the 2 pi in front here, from 1/2 to 1. Y is simply that, all of that, right, in terms of x. So let's put that here. We have x cubed over 6 plus 1 over 2x, and then times all of this underneath the square root, right? So square root of 1 plus 1 over 4 times x squared minus x minus 2 squared, and of course dx. Just remember, this square root, taking the square root of all of this, it just comes from this formula for the ds. Okay, square root of all of that. We have this, we figured it out. Now we take the square root before we plug it into our integral in the form of ds. Okay, so that's just that square root. All right, so now we can simplify this just like before. Let's take the common denominator of the inside here. Okay, so I will start from here. So s would be equal to, let's see, 2 pi from 1/2 to 1 x cubed over 6 plus 1 over 2x. And if we take the common denominator, and what do we get? We get 4 and all of that. So, well, let's simplify this. We have 2 So the common denominator is 4. Then we have 4, and then we have, let's expand this. So we have plus x to the 4th power, right? X to the 4th power here, minus 2 times this times that. We get, the powers are equal and opposite, so they add up to 0, which means the x terms drop out, or they, x to 0 power becomes 1. 1 times 2 minus 2, we get minus 2. Let's see, minus 2, and then plus x2 minus 4 power. Okay, and of course dx. Okay, so now we need to simplify that again, and so let me write that here. We have 2 pi 1/2 to 1. You move this up a little bit. So we end up with, so this should be just 2. My square root should have been a little bit shorter than this, but it's okay, I'll just put it here. I'll just put it here. So square root of 4 is just 2. 4 minus 2 is 2. And we'll get, so we get x to the 4th power plus 2 plus x2 minus 4 power. Okay, and of course dx. All right. So now we can see that these two, this 2 and this 2 cancel out. And once again, just like the previous example, if you take a careful look at the inside of this radical, we can write it as a perfect square. So let's do that. So s equals pi times integral from 1/2 to 1 of this quantity. And this would be x squared, and everything is positive, so plus this one would be x to minus 2 power squared dx. Okay, so that is, so if you expand this, we will get that, because this times that would be just 1 because of the powers, and then 1 times 2 would give us the middle term here, and then the third term from there. Okay, so this simplifies that expression. So let's distribute or cancel the radical with this power. Like that, and dx. So if we just expand everything, distribute the terms, this is what we will get. I always hope I can fit all the solution on one page, but for sure I'm not going to be able to do it here. I'd rather fit the entire solution on one page. So we have, let's see, 1/6. Okay, so if we distribute this x squared into this, we will get 1/6 times x to the 5th power. Distribute this into this 6 with 1 of that will cancel out. We will end up with plus 1/2 x. Now distribute this, we will get x 1/6 plus 1/6 times x, and then of course this would be 1/2 times x to minus 3 power. All of that dx, right? So after distributing the terms. So these are individual terms in x, which should be easy for us to combine and take the integral of. So these two x terms should combine. So let's do that. These two no, but these two should combine. So we have s equals pi 1/2 to 1, and we have 1/6 times x to the 5th. So the common denominator would be 6, and then 3 plus 1, 4/6, or 2 plus 2/3x plus 1/2 times x to minus 3 power dx. Okay, so this is pretty straightforward to find the integral of. Let me remove this. So we have s equals pi times 1/36, right? So 1/36 times x to the 6th power plus 1/3 after simplifying, 1/3 times x squared, and this will be minus 1/4 x to minus 2 power from 1/2 to 1. Okay. Next, let's just do the calculation here. So we have pi times, substitute for x with 1. What do we get? We get 1/36 plus 1/3 minus 1/4 minus, substitute 1/2. So we get, okay, so what did I get for that? Let's see, 1/2304. Please don't take my word for it. See if this agrees with your own calculations. 1/12 minus 1. Okay, so after all of that, this is what I got. So 2,367 divided by 2,304, and then the final surface area is, after simplifying, 263/256 pi. Okay, so these are not too bad of integrals. It's just a matter of applying the right ds formula and the right surface area integral formula. Okay, so let's, and this should be 7. So page 7 here. So here is another example. I will clean this up before posting this on Canvas. But here we have this expression, and this time we want to rotate that region about the y-axis. So remember that on that first slide, if we're rotating about the y-axis, then this is our formula. S equals 2 pi x ds. And then, of course, ds, we can pick whichever one that makes sense. So let me make a note of that. We have, for this, so it would be 2 pi x ds. And then, so let's find the, just like before, let's find the dy dx here. So solution here. And I'm counting on you to pause the video at this point and come up with your own solution first before watching the rest of this. And so, okay, so dy dx would be 1/2, so 2 times 1/4 x 2 minus 1 minus 1 over 2 times derivative of natural log of x is just 1 over x, right? Let's simplify this. So dy dx would be equal to 1/2 x minus 1 over 2x. This is similar to what we had in this previous example, this piece. So we have dy dx equals 1 over 2 times x minus, factoring the 1/2 out, right? And then 1/2 times x minus x to minus 1 power. So let's write it like that. This is helpful when we square all of this. So in the next step, so 1 plus dy dx squared would be equal to 1 plus all of that squared. So we have 1/2 times that, which gives us 1 plus, distribute the power, 1/4 times x minus 1 power squared. Okay, so let's apply our S formula. We have, I'll just put the 2 pi in front this time. 2 pi, we said x, right? We said x, 2 pi x ds. X ds, x range going from 1 to 2. Okay, so this will be, we have S equals 2 pi. Everything here in 1 plus dy dx squared is in terms of x. So in our formula, we don't have to do anything with this. We just keep it. We just keep x. Notice that in previous example, if I bring it back, when we had y, when we had 2 pi y ds, what we did was, because our 1 plus dy dx squared, everything was in terms of x, what we did for y, we replaced it with its equivalent that had all x variables in it, which is that. You see that? For y, we replaced it with this. Here, we don't have to do such thing. We just keep x. Keep it. So x stays as that. And for ds, we're going to multiply it by square root of all of this, right? Square root of 1 plus 1 over 4 times x minus x to minus 1 squared. Of course, dx. Okay, so once again, let me take the common denominator here. So S equals 2 pi times integral from 1 to 2 of x times all of that, 4. So what do we get? We get 4 and then plus all of that, x minus squared dx. Okay. We can now expand this and then combine it with this 4 here. And of course, this will be just 2, right? So let's do that. So S equals 2 pi times, move this up a little bit. So we have, we end up with, just like before, we have 4 plus x squared, right? X squared and then minus 2 times x to minus 1 power. The x terms drop out. We end up with just minus 2 plus x to minus 2 power. Like that. And then, of course, square root of 4 is just 2. Like that. Okay, so what do we end up with? This 2 and this 2 cancel each other out. We have pi times integral from 1 to 2 of x times 4 minus 2 is just 2, x squared plus 2 plus x to minus 2 power. So we have x squared plus 2 plus x to minus 2 power dx. Okay. Once again, this inside can be written in terms of a perfect square. So let's do that. So we have x plus x to minus 1 power squared dx. And of course, the square root and this power cancel each other out. So we have s equals pi times integral from 1 to 2 of x times x plus x to minus 1 power dx. Okay. Now, if we distribute, and I'm trying to keep all the solution on one page, so I hope you don't mind if I squeeze another line here. I'll just say pi and distribute this x into this. Integral from 1 to 2, and we end up with x squared, 1 plus, the power of this is 1, plus minus 1 is 0, so that would be just 1, plus 1 dx. And then if we come up here and continue, what do we have? We have, we can easily integrate this, right? We have pi, so this will be 1/3 x cubed plus x. And of course, this is from 1 to 2. Okay. All right, so let's plug in. What do we get? We have pi times 2 cubed times 1/3 is just 8/3 plus 2 minus 1/3 plus 1, like that. (10/3) times pi. Like that. Okay. So this wraps up chapter 7. We will continue next time with chapter 8, beginning with 8.1. I hope this was worth your time, and I thank you for watching this video until the end. For now, have a nice day, and I'll see you again next time.